March 19th, 1945, somewhere near Paderborn, Germany. Technical Sergeant Robert Earley crouched beside the massive steel hulk, his wrench slipping again on bolts that seemed designed by someone who'd never actually had to turn them. The captured Panther sat motionless in the muddy field, its long 75mm gun pointing uselessly at nothing, its intricate machinery already dying from the inside out. Earley had been maintaining Sherman tanks for 2 years, could swap a transmission in 4 hours, replace an engine in 6. This German masterpiece had travelled less than 100 miles since capture, and already its final drive was grinding itself to pieces. He stood back, shaking his head, watching his crew struggle with the impossible geometry of German over-engineering. They'd stripped away the armour plates, exposing the transmission, and what they found there would change everything they thought they knew about German tanks. This wasn't superior engineering. This was a mechanical suicide note, written in steel. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The Panther tank entered American consciousness on July 10th, 1943, when intelligence reports from the Eastern Front began filtering through Allied headquarters. German propaganda proclaimed it invincible, the answer to Soviet 34 superiority, the future of armoured warfare. On paper, the specifications seemed to justify the boasting. 45 tons of sloped armour that could deflect almost any Allied shell. A 75mm gun with muzzle velocity exceeding 3,000 feet per second, capable of penetrating 4.7 inches of armour at 1,000 yards. Top speed of 34 miles per hour. Operational range of 125 miles. 5-man crew. Sophisticated torsion bar. Suspension. Everything about it screamed technological superiority. Everything except the one number that mattered most, a number American tank crews would discover themselves, written not in specifications but in the broken gears scattered across French fields. 100 miles. That was how long a Panther's final drive typically lasted before catastrophic failure. The story of the Panther's fatal flaw began not in combat, but in a rushed development process driven by panic. After encountering Soviet 34s at the Battle of Brody in June 1941, German commanders recognized their existing tanks were obsolete. The 34's sloped armor, wide tracks, and reliable diesel engine represented a generational leap forward. Hitler demanded an answer immediately. The contract went to MAN, Maschinenfabrik Augsburg-Nürnberg, with impossible specifications. Design a medium tank with heavy tank armor, make it faster than anything we have, arm it to kill any enemy tank at long range, and have it in production within 18 months. The engineers at MAN performed miracles of design, creating elegant solutions to impossible problems. The sloped armor saved weight while improving protection. The interleaved road wheel system distributed load efficiently. The Maybach HL-230P30 engine provided adequate power. The long-barreled gun gave it standoff capability, but in their rush to meet Hitler's deadline, they made one catastrophic miscalculation. They never properly engineered the final drive. The final drive, the gear assembly that transmits engine power to the tracks, is arguably the most stressed component in any tank. It must handle the full torque of the engine, multiplied through the transmission, converting rotational motion into the raw pulling force that moves 45 tons of steel across broken terrain. In the Panther, this critical component was undersized, under-engineered, and fundamentally inadequate for the loads it would face. The gears were too small, the bearings too weak, the housing too fragile. German engineers knew this. Test reports from Kummersdorf Proving Grounds in late 1942 explicitly warned that the final drive design was inadequate. Prototype Panthers suffered final drive failures during trials. Engineers recommended redesign. But Hitler had already announced the Panther would debut at Kursk in summer 1943. There was no time for redesign. Production would proceed with the flawed design. They would fix it in later variants. The fixes never came. Over 5,900 Panthers were produced between January 1943 and April 1945, and every single one carried the same fatally flawed final drive that doomed it to mechanical suicide. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The Panther's combat debut at Kursk on July 5, 1943, revealed the scope of the disaster. Of the 200 Panthers committed to Operation Citadel, 162 broke down before engaging the enemy. Not from Soviet gunfire, from mechanical failure, final drives shattered under the stress of maneuvering, transmissions seized from metal fragments circulating in the oil, engines overheated from the enormous strain of moving a tank whose drivetrain couldn't handle its own weight. Oberstleutnant Wolfgang Schneider, operations officer for the 51st Panzer Battalion, documented the catastrophe in his after-action report. Of our complement of 96 Panthers, only 31 were operational by the end of the first day. 43 suffered final drive failures. 12 had transmission problems. 10 had engine fires. We had not yet fired a shot in anger. The enemy was destroying our tanks with kilometers of Russian steppe, not 34s. This report, classified at the time, circulated through Wehrmacht headquarters, where it was promptly ignored. Hitler refused to believe his wonder weapon was fundamentally flawed. Generals blamed crew incompetence, inadequate maintenance, sabotage, anything except the truth. The Panther was a mechanical failure wrapped in propaganda. American intelligence first obtained a complete Panther in Tunisia, 1943, after German forces shipped a single example for demonstration to Italian forces. When American forces overran the Italian positions, they captured the Panther intact, barely used, and shipped it to the Aberdeen Proving Ground in Maryland for evaluation. What followed was a masterclass in German engineering pretension versus American engineering pragmatism. The evaluation team spent 6 weeks examining every system, measuring every component, testing every capability. Their report, dated November 12, 1943, pulled no punches. The Panther represents sophisticated engineering applied to an inadequately developed design. The sloped armor is excellent, the gun is formidable, the suspension is innovative, the final drive is a disaster waiting to happen. Gear teeth are undersized by approximately 30% for the loads they must handle. Bearing surfaces are inadequate. There is no provision for field replacement. Estimated service life before catastrophic failure, 150 kilometers maximum, likely less under combat conditions. Recommendation: do not attempt to copy this design. The flaws are fundamental and would require complete redesign to rectify. The American approach to tank design provided stark contrast. Sherman tanks were designed from the beginning with maintainability as a core requirement. Every major component could be accessed and replaced by a crew with basic tools. The transmission could be pulled through the front of the hull. The engine could be removed from the rear. Track blocks could be replaced individually. The final drive was massively over-engineered, designed to handle loads far exceeding normal operating conditions, with huge safety margins built in. When American engineers examined the Panther's final drive, they were genuinely shocked. Captain James Thornton, mechanical engineer with the Ordnance Department, examined the captured Panther at Aberdeen and wrote in his personal notes, "This final drive wouldn't be acceptable in a farm tractor, much less a 45-ton tank. The Germans sacrificed reliability for performance specifications. They built a racing car when they needed a truck. This tank will spend more time in maintenance than in combat." His prediction proved devastatingly accurate. By the time of the Normandy invasion in June 1944, American tank crews had heard rumors about Panthers. German tanks with incredible guns and impenetrable armor, monsters that could kill Shermans at ranges where American tanks couldn't even see them. The psychological impact was significant. Sherman. Crews approached every hedgerow wondering if a Panther lurked behind it. The first widespread American encounters with Panthers came during the breakout from Normandy in late July 1944. What crews discovered surprised them. Yes, Panthers could kill Shermans at long range. Yes, Panther armor was difficult to penetrate from the front, but Panthers were also frequently broken down beside roads, abandoned by their crews, or being towed by recovery vehicles. For every Panther destroyed in combat, 2 more were abandoned due to mechanical failure. Staff Sergeant Lafayette Poole, commanding a Sherman named In the Mood with the 3rd Armored Division, described his first Panther encounter near Mortain on August 7, 1944, in a letter to his wife. "We spotted a Panther at about 800 yards. Before we could maneuver for a shot, it stopped moving. We approached carefully, expecting a trap. The crew had abandoned it. We could hear the transmission, grinding even with the engine off. There was oil leaking from the final drive housing. This supposedly superior tank had killed itself. We marked it, destroyed, and moved on." The systematic examination of captured Panthers became a priority for American ordnance teams following the breakout from Normandy. As American forces advanced across France, they encountered dozens of abandoned Panthers. Technical intelligence teams photographed them, measured them, and when possible, transported them to rear areas for detailed analysis. What they found confirmed Aberdeen's predictions and revealed even worse problems. The final drive failure rate was even higher than estimated. Most Panthers were experiencing catastrophic final drive failure between 50 and 100 miles of operation. Some failed even sooner. The problem was compounded by German field modification attempts. Desperate crews, aware their final drives were ticking time bombs, tried various fixes. They over-tightened bearings, which accelerated wear. They used thicker lubricants, which increased friction and heat. They modified gear meshes, which created stress concentrations. Nothing worked. The fundamental problem was that the gears were simply too small and too weak for the loads they had to carry. Lieutenant Colonel Robert Harrison, commanding the 10th Armored Maintenance Battalion, established a specialized team in September 1944 to examine every captured Panther they could find. His team examined 47 Panthers between September and December 1944. Of those 47, 41 showed evidence of final drive failure or impending failure. His report, submitted to Army Ordnance in January 1945, included detailed metallurgical analysis. The final drive gears show evidence of inadequate heat treatment, improper tooth geometry, and insufficient strength for applied loads. Bearing surfaces display severe spalling and wear patterns indicating chronic overload. Housing shows stress cracks from vibrational loads. This is not a design that can be repaired or improved through field modifications. It is fundamentally flawed. The only solution would be complete redesign with larger gears, stronger bearings, and reinforced housing. Such redesign would require 18 to 24 months of development and testing. Germany does not have 18 to 24 months. The human cost of the Panther's mechanical flaws was immense, though rarely discussed. German tank crews didn't just face enemy fire, they faced the constant anxiety of mechanical failure at the worst possible moment. Unteroffizier Hans Becker, Panther driver with the 2nd Panzer Division, described the psychological burden in a post-war interview. "Every time we advanced, I listened to the final drive. Every unusual sound, every vibration, every change in noise meant possible failure. We carried extra gear oil, extra grease, extra tools, knowing they were useless. When the final drive failed, and it always failed eventually, we were helpless. The tank might as well have been destroyed by enemy fire. We would abandon it and march back. Another crew without a tank, another Panther left for the Americans to examine and mock. The mechanical unreliability created a vicious cycle. Crews lost confidence in their vehicles. They became tentative, afraid to maneuver aggressively for fear of mechanical failure. This timidity made them more vulnerable to enemy fire. Meanwhile, American Sherman crews, confident their tanks would keep running, maneuvered freely, using mobility to compensate for armor and firepower deficiencies. The winter of 1944 to 1945 brought new horrors for Panther crews. Cold weather, always brutal on mechanical systems, was catastrophic for the Panther's marginal final drive. Lubricants thickened, increasing friction and wear. Metal contracted, changing clearances and stress patterns. Ice and mud packed into the interleaved road wheels, creating additional loads the final drive couldn't handle. Operational readiness rates for Panther units dropped below 30%. Some units reported less than 20% of their Panthers operational at any given time, not from combat damage, from mechanical failure, from final drives that ground themselves to pieces trying to move tanks through winter conditions. German maintenance crews performed miracles, trying to keep Panthers running. They cannibalized broken tanks for parts. They improvised repairs with inadequate tools and materials. They worked in freezing conditions without proper facilities. But they couldn't overcome fundamental engineering flaws. Master mechanics couldn't redesign components in field workshops. Skilled welders couldn't make weak gears stronger. Dedicated crews couldn't prevent the inevitable mechanical suicide the Panther's design had programmed into every final drive. By early 1945, the Panther's reputation among American tank crews had shifted dramatically. Initial fear had given way to contempt mixed with pity. Yes, Panthers were dangerous if they were running and properly positioned, but running Panthers were increasingly rare. Technical Sergeant Robert Earley, whose crew examined the captured Panther near Paderborn, summarized the American perspective in a letter home in March 1945. The Germans build beautiful tanks that don't work. We build ugly tanks that never stop working. Their Panther is faster than our Sherman on paper. In reality, our Sherman will drive 500 miles, while their Panther limps 100 before breaking down. Their gun is better than ours, but a broken Panther's gun doesn't shoot any straighter than a Sherman's. They've built monuments to engineering pride. We've built tools for winning wars. I know which I'd rather have. The final drive failure rate created strategic effects that cascaded through German operations. They couldn't conduct rapid advances because they broke down. They couldn't conduct fighting retreats because failed final drives immobilized them. They couldn't redeploy between sectors because they wouldn't survive the journey. German commanders found themselves planning operations around mechanical limitations rather than tactical opportunities. Meanwhile, American commanders planned operations, knowing their Shermans would go wherever ordered and keep running until the fuel ran out. The mobility differential, not firepower or armor, increasingly determined outcomes. A Sherman that could maneuver was worth more than a Panther that couldn't move. Generals knew this. Staff officers knew this. But Hitler continued demanding Panther production, convinced that technical specifications on paper translated to battlefield superiority. They didn't. They never had. The Panther's beautiful specifications masked mechanical realities that made it unreliable at best and useless at worst. American factory workers, when they learned about the Panther's mechanical problems through War Department briefings, responded with a mixture of pride and vindication. They'd been building Shermans that were mocked as inferior. Now they learned that German wonder weapons were breaking down faster than American assembly lines could build replacements. Rose Monroe, riveter at the Willow Run plant, recalled a factory floor meeting where supervisors shared intelligence about Panther failures. They told us the Germans were building fancy tanks that broke down after 100 miles. They told us our Shermans were running thousands of miles without major failures. Every rivet we set, every weld we made, we were building reliability into tanks that would outlast anything Germany produced. We worked harder that day than any day before. We weren't just building tanks, we were building proof that American engineering, focused on reliability and maintainability, was superior to German engineering focused on performance and complexity. The mathematical reality of Panther reliability emerged most clearly through maintenance records captured during the final months of the war. When American forces overran German supply depots and maintenance facilities, they discovered meticulous records documenting every Panther's service history. These records, compiled by obsessively detailed German clerks, told a story more damning than any combat report. The average Panther travelled 150 kilometres before requiring major final drive work. The average Sherman travelled 8,000 kilometres before similar maintenance. The ratio was 53-1. For every mile a Panther could travel reliably, a Sherman could travel 53 miles. This wasn't combat effectiveness. This was fundamental mechanical competence, and Germany had failed at it spectacularly. Colonel Ernest Harman, commanding the 2nd Armoured Division, received briefings on captured Panther maintenance records in February 1945. His response captured American sentiment perfectly. The Germans built a sports car and sent it to do a truck's job. Our Sherman is a truck. Trucks win wars. Sports cars sit in garages waiting for parts. His division's Shermans had been in continuous operation since landing at Normandy in June 1944. 8 months of combat, thousands of miles travelled, hundreds of engagements. Yes, they'd lost Shermans to enemy fire. But mechanical failures requiring tank abandonment were virtually non-existent. Engines were swapped, transmissions were replaced, final drives were serviced, but the basic hull kept rolling, kept fighting, kept winning through sheer persistence. The Panther's final drive problem stemmed from a cascade of engineering compromises, each individually defensible, collectively catastrophic. The Maybach HL 230 P30 engine produced 700 horsepower, adequate power for the Panther's 45-ton weight. But the engine's power characteristics, peak torque at high RPM, created enormous stress on drivetrain components during acceleration and maneuvering. The transmission, a sophisticated 7-speed design, was intended to manage these loads through appropriate gearing, but the transmission itself was complex, prone to failure, and heavy. To save weight, engineers reduced the size of the final drive components. This decision, made to meet weight targets, proved fatal. The smaller gears couldn't handle the torque loads, the weaker bearings couldn't handle the radial loads, the thinner housing couldn't contain the vibrational stresses. Every component was marginally adequate under ideal conditions. Under combat conditions, with rapid acceleration, sudden direction changes, and rough terrain, every component was grossly inadequate. American engineers examining captured Panthers marveled at the elegance of individual components while condemning the system integration. The interleaved road wheel, suspension was brilliant, distributing weight beautifully, providing excellent ride quality. But it was also complex, difficult to maintain, and prone to mud and ice accumulation that created additional loads on the final drive. The sloped armor was innovative, maximizing protection while minimizing weight, but the weight savings were spent on the sophisticated suspension and transmission, leaving nothing for the final drive. The gun was magnificent, accurate, and powerful, but the long barrel created balance problems that required additional weight in the turret, which added to the overall weight, stressing the final drive. Every strength created weaknesses elsewhere, every optimization created vulnerability somewhere else. The Panther was a perfectly balanced design on paper. In reality, it was a house of cards where one failing component, the final drive, brought down the entire structure. The contrast with Sherman design philosophy couldn't have been starker. American engineers started with reliability requirements and worked backward to performance specifications. The Sherman's final drive was massively over-engineered, designed with safety factors of 3 to 5, meaning it could handle 3 to 5 times its normal operating loads without failure. This seemed wasteful to German engineers who prided themselves on optimization, using exactly the right amount of material for each component. But American engineers understood something Germans didn't. Combat conditions weren't normal conditions. Tanks would be driven by exhausted crews, maintained by undertrained mechanics, operated in mud, sand, snow, heat, and cold. Components needed margin, they needed forgiveness, they needed to survive abuse and neglect. The Sherman's final drive, crude and heavy by German standards, was nearly indestructible by practical standards. It survived everything the war threw at it. By March 1945, captured Panther examination had become routine for American technical intelligence teams. They'd examined so many Panthers, intact and destroyed, that they'd developed standardized inspection procedures. Check the final drive for metal fragments in the oil. Examine gear teeth for stress cracks and spalling. Inspect bearing surfaces for excessive wear. Measure clearances and compare to specifications. In every case, every Panther examined, the story was the same. The final drive was failing or about to fail. Technical Sergeant Michael Chen, mechanical inspector with the 9th Army's Technical Intelligence Section, examined 37 Panthers between January and April 1945. His report included photographs documenting identical failure patterns. Gear teeth showed stress fractures at the root. Bearings displayed metal transfer and spalling. Housing showed cracks radiating from mounting points. Every failure looked the same, because every Panther had the same fundamental flaw. It wasn't random mechanical failure. It was designed-in, mechanical suicide. The human stories behind the mechanical failures revealed the true tragedy of the Panther's flaws. German tank crews weren't incompetent. They were skilled, brave, and dedicated. But they'd been given tools that would inevitably fail them at the worst possible moments. Feldwebel Kurt Schneider, Panther commander with the 9th Panzer Division, described the helpless frustration in post-war interviews. We would advance toward the enemy, hearing the final drive grinding, knowing failure was approaching but unable to stop it. We couldn't retreat without permission. We couldn't halt for maintenance during combat. We drove forward, listening to our tank destroying itself from the inside. When the final drive finally failed, usually during critical moments, we were helpless. The enemy didn't need to destroy us. Our own engineering had already done that. This wasn't mechanical failure. This was betrayal by our own designers who'd sent us to war in defective machines wrapped in propaganda about German technical superiority. The psychological impact on German crews extended beyond individual breakdowns. Panther crews developed what American military psychologists later termed anticipatory mechanical anxiety. They expected failure. They listened for it. They felt every vibration as potential catastrophe. This constant stress degraded combat performance. Crews hesitated to maneuver aggressively. They avoided rough terrain that might stress the final drive. They conserved movement, trying to extend the inevitable mechanical death sentence their tanks carried. Meanwhile, Sherman crews trusted their machines. They maneuvered freely, confident their tanks would respond. This confidence translated into tactical aggression that often overwhelmed technically superior but mechanically hesitant German forces. The psychological advantage of reliable machinery proved as important as any technical specification. German maintenance personnel faced impossible situations, trying to keep Panthers operational. The final drive wasn't designed for field replacement. Changing it required removing the entire side hull armor, disconnecting the drive sprocket, extracting the failed unit, installing a new unit, reconnecting everything, and reinstalling armor. Under ideal conditions in a rear area workshop, this took 40 hours. Under field conditions, without proper equipment, it was nearly impossible. More often, maintenance crews performed temporary fixes. They drained oil, removed metal fragments, refilled with fresh oil, and hoped the Panther would last another 50 miles. Sometimes it did. Usually it didn't. Hauptfeldwebel Joseph Müller, maintenance chief for the 2nd Panzer Division, documented his unit's struggles in maintenance logs captured near the Ruhr. February 19th, 1945, 14 Panthers assigned, 4 operational, 6 require final drive replacement, no replacements available, 3 require major transmission work, no, parts available, 1 requires engine replacement, no engines available. We cannibalize 3 Panthers to keep 1 running. This is not maintenance. This is mechanical triage where we decide which tanks die so others might live another day. The spare parts crisis compounded the Panther's mechanical problems. Each Panther required specific parts that couldn't be substituted from other tanks. The final drive was unique to the Panther. No other tank used compatible components. When Germany's industrial production collapsed under Allied bombing, Panther spare parts became impossibly rare. By early 1945, many Panther units had more non-operational tanks awaiting parts than operational tanks in combat. The irony was brutal. Germany was still producing new Panthers, albeit in declining numbers, while hundreds of existing Panthers sat immobilized for lack of simple spare parts. Resources went to building new tanks rather than maintaining existing ones. Meanwhile, American maintenance depots stocked thousands of Sherman spare parts. Every component was available, often in multiple variants. Any damaged part could be replaced within hours. The logistics differential between producing spare parts for 5,900 Panthers versus 49,000 Shermans should have been obvious. It wasn't. German logistics never caught up with production. Panthers entered service knowing spare parts wouldn't be available when needed. The final drive's metallurgical problems revealed deeper issues with German wartime industrial quality. When American metallurgists examined failed Panther final drive gears, they discovered inconsistent heat treatment, improper carburization depths, and inadequate material quality. These weren't design flaws, but manufacturing flaws, evidence of an industrial base collapsing under pressure. German factories, bombed repeatedly, staffed by slave labor, lacking quality raw materials, couldn't maintain the precision, manufacturing standards Panther components required. The gears needed careful heat treatment to achieve proper hardness gradients. They needed precise machining to maintain correct tooth geometry. They needed quality steel with proper alloy content. By 1944, they were getting none of these. Gears came from factories staffed by prisoners who had every reason to sabotage production. Heat treatment was rushed or skipped entirely. Steel quality was inconsistent. The result was final drive components that failed even faster than the already inadequate design predicted. American factories faced none of these problems. Workers were motivated, skilled, and working in safe facilities with abundant materials. Quality control was rigorous. Sherman components exceeded specifications consistently. When metallurgists examined Sherman final drive gears, they found proper heat treatment, correct geometry, and quality materials. The over-engineered design, combined with quality, manufacturing created components that simply wouldn't fail under normal conditions. Technical Sergeant James Riley, quality inspector at the Lima Locomotive Works, described the American approach. We inspected every gear before installation. If it didn't meet specifications, it was rejected. We maintained tolerances to within thousandths of an inch. We heat-treated every component properly, tested every batch, documented every process. The Germans were building to minimum specifications with declining quality. We were building to maximum specifications with improving quality. Their Panthers got worse as the war progressed. Our Shermans got better. The operational impact of Panther unreliability showed most clearly in the Ardennes offensive, Germany's last major attack in December 1944. Hitler assembled his final reserves, including several hundred Panthers, for a desperate gamble to split Allied armies and capture Antwerp. The offensive required rapid advance over 100 miles of difficult terrain. For Sherman units, this would have been routine. For Panther units, it was impossible. Of approximately 250 Panthers committed to the offensive, fewer than 100 reached the furthest point of German advance. The rest broke down along the route. Final drives failed on the approach march. Transmissions seized during the initial advance. Engines burned out, pushing through the Ardennes hills. By December 23rd, when American reinforcements arrived and German momentum stalled, more Panthers had been abandoned due to mechanical failure than destroyed by enemy fire. Oberstleutnant Otto Skorzeny, commanding Panther units during the offensive, reported the mechanical catastrophe. We began with 40 Panthers. By December 21st, we had 12 operational, 19 failed mechanically during the advance. 9 were destroyed in combat. We travelled less than 80 kilometers. At this rate, our Panthers would destroy themselves before reaching any objective, regardless of enemy action. The American response to the Ardennes offensive demonstrated Sherman reliability under the worst possible conditions. Patton's Third Army, ordered to turn 90 degrees and drive north to relieve Bastogne, covered 100 miles in 48 hours with over 300 Shermans. They fought through snow, ice, and mud. They engaged German forces repeatedly, and their operational readiness rate at the end of the movement was over 80%. Most Shermans that became non-operational had been destroyed by enemy fire, not mechanical failure. The few mechanical failures that occurred were repaired quickly, using spare parts carried by maintenance units. The Third Army's maintenance battalions followed the advancing Shermans, recovering damaged tanks, repairing mechanical issues, and returning them to service within hours. Meanwhile, German Panther units left trails of abandoned tanks that would never return to service. The engineering lesson was clear, though Germany learned it too late. Complexity isn't sophistication. Optimization isn't superiority. The best design isn't the one with the highest specifications, but the one that works reliably under actual operating conditions. The Panther on paper was superior to the Sherman in almost every measurable way. Thicker armor, better gun, higher speed, more sophisticated systems. But none of that mattered if the tank couldn't move, because its final drive had ground itself to pieces after 100 miles. The Sherman, crude and simple by German standards, worked. It kept working. It worked in conditions that killed Panthers. It worked with inadequate maintenance. It worked when driven by exhausted crews. It worked because American engineers had designed it to work, had prioritized working over theoretical performance, had chosen reliability over optimization. By April 1945, as American forces drove into the heart of Germany, they encountered hundreds of abandoned Panthers. Not destroyed by combat, not scuttled by retreating crews, simply abandoned because they'd broken down and couldn't be repaired. The final drive had failed, or the transmission had seized, or the engine had burned out, and no spare parts existed, and no time remained for repairs, and the crews had walked away from their mechanical monuments to German engineering pride. Technical intelligence teams stopped examining them. There was nothing new to learn. Every Panther told the same story. Sophisticated design, inadequate execution, catastrophic failure. The pattern never varied. American soldiers spray-painted messages on abandoned Panthers. Detroit beats Berlin. Should have bought a Sherman. Nice try, Fritz. The mockery was cruel but accurate. Germany had built beautiful tanks that didn't work. America had built ugly tanks that never stopped working. The final accounting of Panther reliability came from German maintenance records, captured at war's end. Of approximately 5,900 Panthers produced, fewer than 1,000 were destroyed in combat. The rest were abandoned due to mechanical failure or lack of fuel, itself a consequence of mechanical unreliability that limited operational range. The average Panther travelled less than 1,000 kilometres in its entire service life. The average Sherman travelled over 8,000 kilometres before being written off. The reliability ratio was 8-1. For every hour a Panther spent in combat, a Sherman spent 8 hours. The Germans had built a tank that spent more time being repaired than fighting. Americans had built a tank that spent more time fighting than being repaired. In the brutal arithmetic of industrial warfare, reliability mattered more than any other specification. The Panther proved this through its failure. The Sherman proved it through its success. And when Technical Sergeant Robert Earley finally gave up trying to repair that captured Panther near Paderborn, walking away from its frozen gears and shattered drivetrain, he understood what American engineers had known all along. The Germans had lost the war not on the battlefield but in the design office, where engineers had chosen performance over reliability, sophistication over simplicity, specifications over serviceability. The Panther's 100-mile final drive wasn't just a mechanical failure. It was a metaphor for everything wrong with German engineering philosophy and everything right with American pragmatism. The spring of 1945 brought the final chapter of the Panther's story, written not in glorious combat but in pathetic mechanical collapse. As American and Soviet forces converged on Berlin, they found Germany's roads littered with abandoned Panthers, silent monuments to engineering hubris. These weren't battle casualties. These were mechanical corpses, tanks that had committed suicide through their own design flaws. Lieutenant Raymond Griffin, advancing with the 9th Armoured Division through the Ruhr Pocket in April, counted 43 abandoned Panthers along a 20-mile stretch of highway. His report noted something remarkable. Not one showed evidence of combat damage. Every single one had been abandoned due to mechanical failure. Final drives had seized, transmissions had frozen, engines had burned. The crews had simply walked away, leaving their sophisticated machines to rust beside roads they could no longer travel. The human cost of the Panther's unreliability extended far beyond mechanical statistics. German tank crews, among the best-trained soldiers in the Wehrmacht, had their combat effectiveness crippled by machines they couldn't trust. Unteroffizier Hermann Bix, who served in 3 different Panther units between 1943 and 1945, described the progressive demoralization in post-war interviews. In 1943, we believed in our Panthers despite the breakdowns. We thought they were teething problems that would be fixed. By 1944, we knew better but still hoped for improvements. By 1945, we had no faith left. We climbed into Panthers knowing they would fail us, wondering only whether the failure would come during combat or during movement. This psychological burden was as devastating as any enemy fire. American Sherman crews never faced this. They trusted their machines completely. That trust translated into combat confidence that often proved decisive. The spare parts catastrophe that doomed Panther operations revealed the cascading consequences of over-engineering. Each Panther contained thousands of unique components that couldn't be sourced from other vehicles. The final drive alone required 73 different parts, each manufactured to precise specifications, each necessary for operation. When Allied bombing devastated German factories in 1944, the supply chain collapsed. Factories that produced specific Panther components were destroyed. Alternative suppliers didn't exist because components were too specialized. By winter 1944-45, Panther units were cannibalizing 3 tanks to keep 1 operational. The mathematics were brutal and unsustainable. Each month, operational Panthers declined not from combat losses but from mechanical attrition that couldn't be reversed. Meanwhile, Sherman spare parts flowed in endless abundance. Every component was standardized, manufactured by multiple suppliers, stockpiled in massive quantities. A Sherman damaged beyond field repair was simply abandoned. Its crew walked to a depot, drew a new tank, and returned to combat within hours. The metallurgical analysis of failed Panther components revealed something American engineers found almost incomprehensible. German manufacturers were using inferior materials in critical components while maintaining complex manufacturing processes that required superior materials. The final drive gears needed high-quality alloy steel, properly heat-treated, to survive operational loads. By late 1944, they were being made from whatever steel was available, often low-quality material with improper alloy content, inadequately heat-treated in factories operating under impossible conditions. The result was gears that looked correct but failed catastrophically under load. Captain Richard Foster, metallurgical engineer with Army Ordnance, examined Panther components from tanks abandoned during the Bulge Offensive. His report was damning. These gears are made from steel that would be rejected for farm equipment in the United States. The material is inconsistent, the heat treatment inadequate, the quality control non-existent. Germany was manufacturing precision components with materials and processes suitable only for rough construction. The Panther required perfection. Germany could no longer deliver even adequacy. The training differential between Panther and Sherman crews widened dramatically as the war progressed, driven largely by mechanical reliability. American tank crews trained extensively on actual Shermans because thousands were available for training purposes. They learned every sound their tank made, every quirk of its operation, every maintenance procedure. By the time they reached combat, they knew their machines intimately. German Panther crews by 1945 received minimal training on actual tanks because so few were available, and those few were needed at the front. New crews arrived at combat units having never driven a Panther, having never fired its gun, having never performed maintenance. They learned in combat, where mistakes were fatal. Gefreiter Wilhelm Hoffmann, assigned to a Panther unit in March 1945 at age 17, described his training. "I sat in a wooden mock-up for 2 days, memorized the controls from diagrams, and was then assigned to a Panther as driver. My commander had been a crew member for 3 weeks. Our gunner had fired 5 practice rounds. We were children playing with machinery we didn't understand, facing enemies who knew their equipment perfectly." The maintenance philosophy differences between German and American forces showed most starkly in their approach to non-critical failures. When a Sherman developed a minor problem, a leaking seal, a loose connection, a worn bearing that still functioned, crews noted it and continued operating. The problem would be fixed during scheduled maintenance or when convenient. The Sherman's robust design allowed continued operation despite minor defects. When a Panther developed any problem, operations became questionable. The tightly optimized design meant every component operated near its limits. A minor oil leak could lead to inadequate lubrication and catastrophic failure. A loose connection could cascade into system breakdown. A worn bearing could seize suddenly. Panther crews couldn't ignore minor problems because minor problems became major failures without warning. This meant Panthers spent enormous time in maintenance for problems that wouldn't even be noted in a Sherman. The operational availability differential grew not just from major failures, but from the cumulative impact of thousands of minor issues that grounded Panthers while Shermans kept running. The final drive failure pattern showed remarkable consistency across all Panther variants and production periods. Whether early production Panthers from 1943 or late production models from 1945, whether built at MAN factories or Daimler-Benz facilities, whether operated on the Eastern Front or Western Front, the failure mode was identical. The final drive would begin making noise, a grinding or whining sound that crews learned to recognize with dread. The sound would worsen over 20 to 50 miles of operation. Then would come violent vibration as gear teeth began, breaking. Finally, catastrophic failure as gears disintegrated and the final drive seized completely. The entire process, from first warning to complete failure, typically took less than 100 miles. Experienced crews could predict failure timing with grim accuracy. New crews often pushed their Panthers past the warning signs, trying to complete missions, and suffered catastrophic failures at the worst possible moments during combat or while retreating under fire. American technical intelligence compiled comprehensive statistics on Panther reliability by war's end. They'd examined over 200 captured or abandoned Panthers. They'd interviewed dozens of captured German tank crews. They'd analyzed maintenance records from multiple Panther units. The conclusions were unambiguous and devastating. The Panther OSF-D, first production variant, achieved approximately 100 kilometers mean distance between final drive failures. The Panther OSF-A, supposedly improved, achieved approximately 120 kilometers. The Panther OSF-G, final production variant with various improvements, achieved approximately 150 kilometers. 3 years of production, supposedly incorporating lessons learned and improvements, had increased final drive reliability by 50%. But 50% of inadequate was still inadequate. Meanwhile, Sherman final drives were achieving 8,000 to 10,000 kilometers between major services. The reliability ratio actually worsened as the war progressed, because Sherman reliability improved through manufacturing refinement, while Panther reliability declined through material and quality control deterioration. The strategic implications of Panther unreliability extended beyond individual tank operations. German commanders found themselves unable to conduct mobile warfare, the very doctrine that had brought them victory in 1939 through 1941. Rapid advances were impossible when tanks broke down after 100 miles. Strategic redeployment between fronts couldn't be executed when half the tanks would be abandoned en route. Counterattacks lost momentum when attacking forces left trails of broken Panthers. By 1945, German armored forces were effectively immobile, capable of static defense but incapable of the mobile operations that armor was designed to enable. American forces faced no such limitations. Sherman reliability enabled the rapid advances from Normandy to the Rhine, the lightning relief of Bastogne, the race across Germany. American commanders could plan operations knowing their armor would go where ordered and arrive ready to fight. The economic analysis of Panther versus Sherman revealed another dimension of the reliability disaster. Germany invested enormous resources in Panther production. Each tank required approximately 300,000 man-hours to build, consumed rare materials, including substantial quantities of molybdenum and tungsten needed for armor and ammunition, and tied up manufacturing capacity that could have produced 3 or 4 Panzer IVs. This investment was then abandoned after less than 1,000 kilometers of operation when the final drive failed and no spare parts existed for repair. The return on investment was catastrophically poor. America invested far fewer resources per Sherman, approximately 48,000 man-hours using common materials and existing manufacturing infrastructure, and received operational lives exceeding 8,000 kilometers. The return on investment was spectacularly good. Purely from an economic perspective, the Panther was a disaster, consuming resources without delivering proportional combat value. The Sherman was a triumph, delivering combat value far exceeding its resource cost. The post-war analysis by German military historians and engineers involved extensive self-examination about how the Panther disaster had occurred. The Panther consensus pointed to several systemic failures. First, the rush to production, driven by Hitler's demands, prevented adequate testing and development. Engineers knew the final drive was inadequate, but weren't given time to fix it. Second, the refusal to accept feedback from field units meant problems were never addressed. Reports of final drive failures were attributed to crew incompetence or battlefield conditions rather than design flaws. Third, the emphasis on technical specifications over practical reliability reflected a cultural bias toward engineering elegance rather than functional sufficiency. German engineers wanted to build the best possible tank. American engineers wanted to build a tank that worked. The cultural difference produced the reliability gap. General Franz Halder, former German Army Chief of Staff, wrote in his post-war memoirs that the Panther exemplified everything wrong with German weapons development in World War II. Brilliant designs rushed into production, inadequately tested, impossible to manufacture in quantity, too complex to maintain in field conditions, and ultimately unsuccessful because reliability matters more than sophistication. American engineers studying captured Panthers drew different lessons that would influence U.S. tank design for decades. Simplicity enables reliability, redundancy provides safety margins, standardization facilitates logistics, maintainability determines operational availability. These principles, proven by Sherman's success and Panther failure, became foundational to American military equipment design. The M48 Patton tank of the 1950s, the M60 tank of the 1960s, even the Monet Abrams tank of the 1980s, all reflected lessons learned from the Panther disaster. American tanks prioritized reliability over maximum performance, maintainability over optimization, proven technology over innovation. The Abrams tank uses a gas turbine engine that is technologically less efficient than diesel but more reliable in operation. This design choice echoes the Sherman philosophy. Better to have a tank that works than a tank with superior specifications that doesn't. The human stories of Panther crews facing mechanical failure in combat revealed courage and frustration in equal measure. These were skilled soldiers, well trained by 1943 standards, brave and determined, let down by machines that couldn't fulfill their promise. Feldwebel Ernst Bachmann, who achieved numerous tank kills in his Panther and survived the war, reflected bitterly on the mechanical failures he'd witnessed. For every engagement where my Panther performed magnificently, there were 3 occasions where it failed mechanically at critical moments. I watched friends die because their Panthers broke down during combat. I saw brilliant tactical plans collapse because our tanks couldn't move. The Americans never faced this. Their Shermans kept running. Reliability isn't glamorous, but it wins wars. We had glamorous tanks that lost. They had unglamorous tanks that won. The mathematics were simple, even if we refused to see them. The Soviet experience with captured Panthers provided independent confirmation of their mechanical problems. Soviet forces captured hundreds of Panthers on the Eastern Front and attempted to press them into service. The results were disastrous. Soviet maintenance crews, accustomed to the simple, robust 34, found Panthers impossibly complex and unreliable. Soviet tank crews, used to tanks that worked despite abuse and neglect, found Panthers required constant, careful maintenance they couldn't provide. Most captured Panthers were abandoned after brief use. Soviet after-action reports were scathing. The German Panther represents engineering divorced from practical reality. It requires specialist maintenance, constant attention, and abundant spare parts. Under combat conditions, it is inferior to our 34 in every meaningful way because it cannot be kept operational. The Soviets, like the Americans, learned that reliability trumped specifications. This lesson informed Soviet tank design for the rest of the Cold War. Soviet tanks were simple, crude by Western standards, and almost indestructible in operation. By May 1945, as the war ended, the Panther's legacy was clear and damning. Of approximately 5,900 produced, fewer than 100 remained operational. The rest had been destroyed in combat, abandoned due to mechanical failure, or cannibalized for parts. The final drive failure rate had never improved. The spare parts situation had never resolved. The training crisis had never been addressed. The Panther entered service flawed and exited service flawed, teaching painful lessons about the difference between engineering excellence and operational effectiveness. Meanwhile, tens of thousands of Shermans remained in service, equipping armies around the world, continuing to operate reliably for decades after the war ended. Some Shermans saw combat in the Korean War in 1950 through 53, 6 to 8 years after production ended, still running reliably. Some served in armies into the 1970s, 30 years after their production, still functional. The Sherman's design, mocked by German engineers as crude, proved more enduring than the sophisticated Panther that couldn't survive 100 miles. The final judgment on the Panther came not from historians or engineers, but from the soldiers who'd fought in and against it. At a 1978 reunion of tank veterans in Germany, American and German crews met to discuss their experiences. The conversation turned inevitably to the Panther versus Sherman debate. Oberfeldwebel Otto Carius, Germany's most successful tank ace with over 150 kills, acknowledged what German propaganda never had. The Panther was mechanically magnificent when it worked, which was rarely for long. We spent more time fixing Panthers than fighting in them. The Americans spent more time fighting in Shermans than fixing them. They won through reliability. We lost despite sophistication. Staff Sergeant Clarence Smoyer, who'd fought through Europe in a Sherman, added the American perspective. We didn't need to beat Panthers in single combat. We needed to outlast them. Our Shermans kept running when their Panthers stopped. Persistence beats perfection in war. That's what we learned. That's what they learned too late. The story of the Panther's 100-mile final drive is ultimately a story about choices and consequences. Germany chose performance over reliability, sophistication over simplicity, theoretical excellence over practical sufficiency. These choices produced a tank that looked magnificent on paper and failed catastrophically in reality. America chose reliability over performance, simplicity over sophistication, practical sufficiency over theoretical excellence. These choices produced a tank that looked mediocre on paper and succeeded spectacularly in reality. The war proved which philosophy was correct, not through dramatic tank duels, though those occurred, but through the grinding arithmetic of operational availability. Shermans were available when needed, Panthers weren't. Everything else was commentary on that fundamental fact. The Panther's legacy lives on not as an example of German engineering excellence, but as a cautionary tale about the dangers of prioritizing specifications over serviceability, complexity over reliability, perfection over adequacy. Engineers still study the Panther when learning what not to do. The 100-mile final drive remains history's most expensive object lesson in why reliability matters more than any other specification in military equipment. Germany built a beautiful tank that didn't work. America built an ugly tank that never stopped working. The ugly tank won the war. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.